examples from section 6.4. I'm going to be doing some even problems. You'll be doing some odd problems for your assignment. So for all of these, they give you a function for y, and all of the functions are integrals, and we are asked to find dy dx. So it's the setup for using the fundamental theorem of calculus. Because we are trying to find the derivative of an integral, we need to make sure the derivative matches the upper limit of integration and that the lower limit of integration is a constant. So we are finding dy dx, so d dx of the integral. The lower limit is a constant. The derivatives match. The derivative matches the upper limit of integration. So then we have this set up to where all we have to do is plug it in. And we're done. On number 4, again, we're finding dy dx. So we're finding d dx of the integral. The the derivative matches the upper limit. Lower limit's a constant, so we just plug it in. So we get 1 plus e to the 5x. Okay, number 6, dy dx. So derivative of an integral. The integral matches the upper limit, and the lower limit's a constant, so our answer is e to the x secant x. Next one, finding the derivative, dy dx. So the derivative of an integral. Notice the lower limit is a constant, the upper limit is an x, which matches, so we can just plug this in, and we get 2 minus sine x over 3 plus cosine x. Next one, derivative of an integral. Okay, now the lower limit is a constant, so that's good, but notice this is not just an x. We're still going to plug in the x squared. So we get cotangent 3x squared, but then we have to take the derivative of this, which is 2x. So then my answer is 2x times cotangent 3x squared. Okay, on the next one, again, taking the derivative of an integral. The lower limit is a constant, pi is a constant. The upper limit involves an x, but it's not just an x, so I'll have to use the chain rule. So I start by plugging in the value. So we have 1 plus sine squared pi minus x over 1 plus cosine squared pi minus x. But then because it wasn't just an x, I have to take the derivative, which would be -1. So I'm just going to write it like that. Number 14, we are taking the derivative of an integral. But notice the lower limit is not a constant, the upper limit is. So this is one where I have to switch the limits of integration. So I'm going to make it the opposite and switch this. And then now we have the setup, so we can plug it in. So we're going to have a negative square root 2x to the 4th plus x plus 1. Next problem. Okay, so on this one, the constant's in the numerator, or in the upper limit. So I am taking dy dx, so I'm taking the derivative of an integral, but I'm going to have to switch this. So I can have the 25 as the lower limit. Okay, so I have that set up, and they match, except it's not just an x. So I am going to involve the chain rule. So I am going to have a negative, and I'm just going to kind of put that out front. And then we'll have, we're going to plug in a 5x squared. So we're going to get 5x squared, and that's squared, minus 2 times 5x. Actually, I'm going to do this. 5x squared. And then we have a plus 9 all over. And then instead of a t cubed, we're going to put a 5x squared cubed plus 6. And then we have to do, because it wasn't just an x, we have to take the derivative of this, which is the derivative of 5x squared, is 10x. Okay, so now I'm just going to simplify and be really careful. I'm going to distribute the negative sign, and at the same time, I'm going to distribute the 10x. So when I do that, we're going to have 10x. Here I square the 5, so I get 25x to the 4th. So that's going to be a negative 250 x to the 5th. I might regret this. So then this is going to make this a plus, and that's going to be 10x squared times 10x is 100 x cubed. And then we're going to have this is going to make that a minus 9, but then times 10x is going to be minus 90x. And the denominator, this is going to be, we have to cube the 5, so we get 125 power to a power, multiply the exponents, plus 6. Okay, and just to make sure I didn't make a careless mistake, I checked the answer book. So that we agree there. But yeah, I might not have wanted to do that in one step. So hopefully you followed that. Number 18. Okay, so we are again finding dy dx still. So we're taking the derivative of an integral. Now notice on this one, neither one of them have a constant. So this is one where we're going to split it apart. So I'm going to split it apart from 3x squared to 0 of ln 2 plus p squared dp plus from 0 to 5x ln 2 plus p squared dp. Now, this one is good except for the chain rule, remember. This one I have to switch. So I'm going to make that negative, and then from 0 to 3x squared. And leave this one alone. And I really should have my ddx. I forgot that. Okay, so now we have the setup. Don't forget the chain rule though. So we're going to have a negative ln 2 plus, we're squaring this, so we're going to have a 9x to the 4th. But then I have to multiply by the derivative, which is 6x, plus, and over on this side we're going to have ln 2 plus, we're squaring this, so we get 25x squared. And then the derivative of 5x is 5. So we could write this as negative 6x ln 2 plus 9x to the 4th plus 5 ln 2 plus 25x squared. So when you look at the function, it looks really scary and complicated. But when you use the fundamental theorem of calculus, it makes it so easy. You do have, I mean, they can get a little complicated as far as things you're plugging in and making sure you don't make any mistakes by forgetting the chain rule or, distributing any negative signs, whatever you need to do. But the fundamental theorem of calculus makes it so much easier. Okay, so the last one I was going to do here, we're doing the same thing. Okay, I have to split it apart, so I'm going to go from sine x to 0 of t squared dt plus 0 to cosine x t squared dt. Again, you don't have to use 0, it's just convenient. So I'm going to switch this, so my constant's at the bottom. And here I can leave it alone. And now I can plug that in, but remember, you're going to have to use the chain rule. So we're going to end up with negative. When we do sine x quantity squared, we write it this way, sine squared x. But then I need the derivative of sine x, which is cosine x, plus, here we're going to substitute that in, and so we get cosine squared x, but then I need the derivative of cosine x, which is negative sine x. So I'm going to rewrite this as negative sine squared x cosine x minus sine x cosine squared x. Okay, so that should take you through your first assignment. You should be able to get those done.